Okay, again repeat. So this one and this one will continue continuous up to infinity. Okay, so this is the waveform of the half wave rectifier. Okay, half wave rectifier. If we connect half wave, okay, now if we connect okay, this is the waveform of full wave rectifier. Okay, half wave rectifier. Okay, now we'll find out what is the V average. What is the V average of this half wave rectifier? What is the V average of the half wave rectifier? So V average derivation. Okay, V average and VRMS of half wave whatever. Okay, this is a circuit diagram working. Okay, waveform. Now we'll derive V average and VRMS. Okay, so V average, what is the formula for this? What is the time period of this? What is the time period of this waveform? What is the time period of this waveform? How much? 2 pi. Time period of this waveform is 2 pi. Okay, so now V average is equal to 1 by 2 pi integral 0 to 2 pi m sin omega t d omega t. Okay, so here 0 to 2 pi, 0 to 2 pi. See, 0 to pi we are getting output. Pi to 2 pi we are not getting output. So we are now dividing this one. Okay, so 1 by 2 pi. I am dividing now 0 to pi Vm sin omega t plus pi to 2 pi. Pi to 2 pi 0 d omega t. Why? Because only 0 to pi only we are getting the value. Whereas pi to 2 pi, see, pi to 2 pi, what is the value? 0. Okay. 0 to pi we are having the value. Pi to 2 pi we are not having the value. So, okay. So integration of 0, you will get 0. So here now 1 by 2 pi 0 to pi Vm sin omega t d omega t. Okay. Now, so because of Vm is a constant in this Vm sin omega t, Vm is a constant. We cannot change. So bringing this constant outside from the integral. So it will become now Vm by 2 pi integral 0 to pi sin omega t d omega t. Okay. So here see integration of sin will become minus cos. So here Vm by pi minus cos omega t pi and 0. Okay. Now this will become Vm by pi, Vm by 2 pi, Vm by 2 pi. Okay. Minus of cos pi and minus of minus plus cos 0. Okay. So by applying this, we will get here Vm by pi. Here cos pi minus 1 of minus 1 plus 1 and plus cos 0 1. Okay. So we will get here 2Vm by 2 pi. So 2 will get cancelled. We will get Vm by pi. So this is the average value of half wave rectifier. Average value of half wave rectifier. What is the value? Vm by pi. Okay. Now after this we'll find out RMS value of half wave rectifier. RMS, this is average value. RMS value of half wave rectifier. Okay. I will write here RMS value. So VRMS. What is the abbreviation of RMS? What is the abbreviation of RMS? Root mean square. So here root mean 1 by 2 pi integral 0 to 2 pi Vm square sin square omega t d omega t. Okay. Now here root mean square. So root of 1 by 2 pi. Here we will get only 0 to pi only. Vm square sin square omega t d omega t. Okay. Plus pi to 2 pi. 0 d omega t. I am dividing this. Why? Because we are getting only up to 0 to pi only. Pi to 2 pi the value is 0. Now after this Vm square is a constant. Okay, bringing out. So 1 by 2 pi Vm square by 2 pi under root. Okay, integral 0 to pi sin square omega t d omega t. Okay, what happened to this term? This term will become 0. Pi to 2 pi, the term is becoming 0. Okay. Now after this, I am writing here, see the formula is sin square theta. I am able to write down 1 minus cos 2 theta by 2. Okay. So here I am substituting this under root Vm square by 2 pi 0 to pi 1 minus cos 2 omega t by 2. Okay. So no need to worry for this. This is whether 1 minus cos omega t or 1 plus cos omega t. Okay. Why? Because cos 2 theta always will become 0. Cos multiple of angles will become 0. So it may be 1 minus cos 2 omega theta or 1 plus cos 2 omega theta. No need to worry for this. Okay. Into d omega t. So here 1 by 2 is the constant. We are bringing constant outside. Okay. So here it is nothing but 1 by Vm square. Already 2 is there. 4 pi under root integral 0 to pi 1 d omega t minus integral 0 to pi cos omega t. Cos 2 omega t. Okay. And d omega t, d omega t, d omega t. Okay. Now which will become now cos 2 theta. Cos 2 theta always will become 0. Only the term left is under root of Vm square by 4 pi. Here pi minus 0. So this pi get cancelled. Okay. We left with a Vm square. 2 root cancel. 4 root cancel. We will get a Vm by 2. Vm by 2. Okay. So RMS value is RMS value is Vm by 2. Average value is Vm by pi. Okay, so this is about a total half wave rectifier. You have to explain about this thing. Circuit diagram, working, waveform, average value, RMS value. Okay. So in exam, whenever there is a circuit diagram, draw the circuit diagram neatly. This circuit diagram they will see. Waveform they will see. If derivation is there, derivation they will see. You are writing some sentences that nobody will see. Okay. Only circuit diagram is important. Circuit diagram is correct, then you will get a 50% of marks. If you are unable to draw this circuit diagram, no, no one will give the marks. Why? Because how the functioning of the circuit, okay, circuit will be explained here. If circuit is wrong, how can we explain the circuit functioning? We are unable to. That's why, okay, what is this? AC supply. After this, DC supply. DC. Okay. So this is about full total half wave rectifier. So this semester you will get a full wave rectifier, not half wave rectifier, full wave rectifier. We may expect. Okay. So now we'll study full wave rectifier. Okay. Why you are calling half wave rectifier? Only half of the wave is converting. Negative wave it is not converting. That's why half wave rectifier. Okay. Right. Now full wave rectifier. Hmm? So circuit diagram will full wave rectifier. So same circuit diagram, 230 volts AC supply of 50 hertz. So full wave rectifier. So here instead of using single diode, you will use two diodes. We'll use two diodes. So this is called diode 1, this is called diode 2. Okay, diode 1 and diode 2. What happened actually? See, here so this is about a full wave rectifier. Full wave rectifier. Okay. So instead of using single diode, you will use two diodes. Okay. This is the input we are giving. So here we are able to convert positive and negative. Positive and negative. See. So here during the positive half cycle. During the positive half cycle, what happens? During positive half cycle, during positive half cycle, this will become positive, this will become negative. Transformer secondary terminals will become positive and negative. So it means diode 1. Okay. During positive half cycle, diode 1 on and diode 2 off. Diode 1 is on, diode 2 is off. Why? During positive half cycle, okay, this will become positive, forward mode. This will become reverse bias. Okay, it means the circuit will be now, okay, D1 on, D2 off. Here, secondary, during positive half cycle, the current will flow from like this. So positive to negative, positive to negative. Okay, so during positive half cycle, what happens? Current will flow from D1 to load. What happened to this? D2 is off. There will not be any current flow. Okay, circuit will become, okay, D1. Okay, so this is the output waveform. Okay, so here same. So at this condition, D1 on, D2 off. Okay, in negative half cycle, okay, what happens? This will become minus, this will become plus. So in negative half cycle, what happens? In negative half cycle, what happens? D1 off, D2 on. It means negative half cycle. See, minus terminal is applicable to diode P. Here plus. Here it is plus, it is minus. And during negative half cycle. So D1 is off, D2 is on. It means forward. Okay. So D1 is in reverse bias mode, D2 is in forward bias mode. Okay. So what happened? The circuit will be now. So the current will flow like this. Okay. So see how the current direction in both cases, how the current direction with respect to resistor, positive to negative, positive to negative, positive to negative, positive to negative. So here during negative half cycle also will get a positive curve only, positive. Okay, positive. And again here D1 off, D2 on, and so on, which will repeat. Okay, see D1 on, D2 off, same, which will repeat. Okay, D1 off, D2 on. And this process will continuously. Okay, why? Because positive cycle, negative cycle, positive cycle, negative cycle, positive cycle, negative cycle, and up to infinity. So positive cycle, this will happen. D1 will get on in negative half cycle, D2 is getting on. So simultaneously D1 and D2 get a switching on, switching off, switching on, switching off. So thereby we will get a continuity of supply. This is the continuity of the supply. Okay, continuity of supply. In previous case, half of the cycle we are unable to convert. It is getting 0. But here, no. Okay, what is the time period now? What is the time period? What is the time period? So time period is pi. Full wave rectifier time period is pi. Okay, why? Because it is repeating at a pi only. 0 to pi, it is repeating. Okay. Pi to 2 pi also pi only. 2 pi to 3 pi also pi only. So it is repeating. Okay. So now we'll find out a V average. V average for half wave rectifier. So V average is nothing but 1 by, what is the time period? Pi. Okay. 0 to pi. Vm sin omega t d omega t. Okay. Now, so now here Vm is constant. I am bringing out from the integral. So integral 0 to pi sin omega t d omega t. Okay. So now here Vm by pi. So integral sin theta is nothing but cos theta. So minus cos omega t. Okay. Pi 0. So now Vm by pi minus of minus 1 minus of minus 1 plus 1. So it will become now 2 Vm by pi. 2 Vm by pi. So V average is now 2 Vm by pi. Okay. So average value of the full wave rectifier is 2 Vm by pi. Okay. Now we'll find out RMS value of full wave rectifier. RMS value of full wave rectifier. Okay. Okay. What is the formula RMS value? Root mean square. Okay. So now here what are constant? Vm square is constant. I am bringing Vm square out by pi under root of 0 to pi sin square omega t d omega t. Okay. So here I am writing sin square omega t in terms of 1 minus cos 2 theta by 2. So here Vm square by pi 0 to pi 1 minus cos 2 omega t by 2 d omega t. So 2 is common. So constant. So I am bringing this one is out of the integral. So Vm square by 2 pi integral 0 to pi 1 d omega t minus integral 0 to pi cos 2 omega t d omega t. Okay. So from this, what will happen? This will get cancelled. We'll get only Vm square by 2 pi. Okay. Vm by 2 pi into pi minus 0. Okay. So from this, pi get cancelled. Vm square and root cancel. So Vm by root 2. So Vm by root 2 is the answer. So average value of full wave rectifier is Vm by root 2. What the average value? Average value is 2 Vm by pi. Okay. After getting average value and RMS value, we'll find out form factor. Form factor. Okay. What is the formula for form factor? Form factor. Form factor is equal to VRMS by, it is the ratio of VRMS by V average. Find out form factor, VRMS by V average. VRMS is Vm by root 2. V average is 2 Vm by pi. Find out. So form factor is now form factor is okay is equal to VRMS by V average. So VRMS is Vm by root 2. V average is 2 Vm by pi. Okay. Now Vm by root 2 into pi by 2 Vm. How much it is? 1.11. So form factor of full wave rectifier is 1.11. So after this waveform, actually we have to connect a filter. Full wave rectifier with filter. Your filter is not there. Okay, half wave rectifier with filter. Connect a capacitor across the resistor. Okay, which will become now half wave rectifier with filter. Connect capacitor. Okay, wherever capacitor is there for half wave rectifier, you connect there capacitor, which will become half wave rectifier with filter. Here connect a capacitor across the, here you connect a capacitor. Connect this combination is now, this is the load here. I'm connecting capacitor. So capacitor is nothing but by adding capacitor. What do you mean by capacitor? See, is it straight line? No, it's not a straight line. So draw the straight line here. So straight line. So actually DC means straight line, but we are unable to get the DC. So this area is called ripples. This area is called ripples. That area can be removed by adding a filter. So ripple the filter. Okay, it is a filter. We can call it as this capacitor is a filter now. Half a full wave rectifier with filter. By adding a capacitor across the load, the circuit will become as okay rectifier circuit with a filter. Okay, right. Now by connecting the filter, what happened by connecting the capacitor? What happens? Which will remove the ripples content of the output waveform. So by connecting the capacitor, what happened? The output waveform will not be like this. Now, after filter, after connecting the filter, okay, diode is there, diode 1 is there, diode 2 is there. But additionally, we added one capacitor. So the output waveform is not like this. This is not output waveform. The output waveform is like this. Okay, so this is the output waveform. It is not going towards the 0. So it is going towards the 0. 0. At this point it is getting 0. At this point it is getting 0. At this point it is getting 0. Okay, but by adding the capacitor, the content of the rippleness we removed. So it is not going to 0 now. 0 avutunda? No, it is not getting 0. Okay, so here also it is not getting 0. This is the output waveform of full wave rectifier after filter. This is the output waveform. See whether it is getting 0. No, it is not getting 0. See, if it is touches here, it is getting 0. It is not getting 0. So by adding a appropriate capacitor, okay, by adding the appropriate capacitor, or by adding the design of filter should be good or efficient, then this curve also will be look like now. This curve is how it is look like now. It is by adding a good capacitor, by adding a good filter. So this curve will become like this. Okay, we can say it is a not exactly appropriately, it is a straight line. Yes, it is a straight line. So now we converted AC to DC. AC to DC. Okay, this is about a half wave rectifier and a full wave rectifier. So we may expect this full wave rectifier in the exam. Okay. Now, once you see the syllabus, what are the topics we covered yesterday and today? Huh? Once you see the syllabus, we covered almost all. Wait. See, if you see the previous question paper, see previous question paper, explain the applications of rectifier and amplifier. And what is gray code? Explain in detail. Yesterday we studied about gray code. Yes. What are the difference between combinational and sequential circuits? Explain the basic theorems of Boolean algebra. Yesterday we written them theorems. That is Boolean algebra theorems. Okay. And then discuss about functionality of a AND gate with a truth table. Okay, so all the gates yesterday we completed, and Boolean algebra, that is theorems, also completed. Gray code and whatever the unit 3, okay, everything we completed. Rectifiers now we completed. Amplifier only is asking about applications. So here we'll see, right. So we'll study now. Okay. What is mean by PN junction diode? What is its characteristics? What is mean by general diode? What is its characteristics? And what is mean by BJT? How can we connect this BJT? Okay, how can we connect a bipolar junction transistor in a CB configuration, CE configuration, okay, CC configuration? Okay, with this we'll cover all the topics. Yesterday we covered the about regulator power supply. Regulator power supply, did we complete it? Yesterday, regulated power supply and public address system completed. So these are all also very, very important. Public address system, regulated power supply, its block diagram, its working. Okay, individual block, what is the function of that individual block? Also important. Okay, regulated power system, public address system. Okay, and Hamming code also we studied. Gray code, BCD code, XS3 code. Okay. Boolean algebra, addition, subtraction, multiplication also we have done. Okay. So kindly read these all topics. We'll now move on to, okay, PN junction diode characteristics, general diode characteristics, and general diode as a regulator. Okay. What are the applications of this rectifier? Applications of the rectifier. So rectifiers are used in chargers, or phone chargers are there na. In the charger we are having the rectifier. Okay. So wherever we require DC supply. Okay. For example, RPS, regulated power supply, will use the rectifier. Okay. Wherever we require, in TVs also, in TVs we require DC supply. Okay, wherever we require DC supply, there we will use the rectifiers. Okay, amplifiers. Where will use amplifiers? Amplifiers is used in a telecommunication. In telecommunication, and amplifiers are used in, okay, not amplifiers. Amplifiers. Yes, amplifiers used in public address system also. Amplifiers used in public address system. So application is amplifiers. Rectifier is, okay, wherever we require AC to DC, for example, charger, okay, in the electrical circuits where we require AC to DC, there will use rectifiers. Amplifiers means in public address system we'll use the amplifier where we signal smooth, and all electronic communication system also will use the amplifiers. Okay, right. సార్ అది యూనిట్ 1 అని ఉంటుంది చూడండి. యూనిట్ 1 కాదు, యూనిట్ 4 జస్ట్ నౌ యూ ఓపెన్. So just you want to know about PN junction diode. What is mean by PN junction diode? What is mean by general diode? Why we are calling as P? యూనిట్ 4 జస్ట్ ఈరోజు మార్నింగ్ ఓపెన్ చేసిండ్రు కదా. యూనిట్ 4 ఈరోజు మార్నింగ్ ఓపెన్ చేసిండ్రు కదా. So in this we'll study, okay, this is part B, unit 1, PN junction diode, general diode, and Okay. What is mean by PN junction diode? What is mean by P? So P is nothing but one type of material. P type material. What is mean by P type material? What is mean by P type material? So PN junction diode. So whenever P type material is sandwiched to N type material, which will form the PN junction diode. Okay. P-type material is sandwiched to N-type material, which will form the PN junction diode. What is meant by P-type? What is meant by P-type material? What is meant by P-type material? Okay. See, we know how many type of materials we are having. One is, we can say, conductor. Second one is called semiconductor. Third one is called insulator. Conductor, semiconductor, insulator. A lights object. So, conductor, semiconductor, insulator. So, these are the three materials we are having. So, generally we will use the, for manufacturing of all the electronic devices, we will use the semiconductors like silicon and germanium. Okay, depending upon the materials, depending upon the, okay, semiconductor material, okay, semiconductor materials are further classified as intrinsic semiconductor and extrinsic semiconductor. Okay, here I'm explaining about what is mean by P-type material. What is mean by P-type material. Okay, so so here intrinsic semiconductors are there, extrinsic semiconductors are there. What is meant by intrinsic semiconductor? Pure form of material. Pure form of material is known as intrinsic semiconductor. Okay, pure form of material is known as intrinsic semiconductor. Okay, if we add some impurities, if we add some more material, that is called impurities. Okay, adding of impurities. Okay, I will add the impurities to the intrinsic semiconductor, which will become extrinsic semiconductor. Okay, what is meant by extrinsic semiconductor? Pure form of, so intrinsic semiconductor plus impurities is known as extrinsic semiconductor. Okay, okay. So here, so what is meant by P-type material? వస్తుంది కదండి నెక్స్ట్కి వెళ్ళండి. So what is meant by P-type material? What is meant by N-type material? I will tell. Okay. So this everything you know. So this is the diode. So diode. Generally, the brief idea. This is PN junction diode. It is in P-type material, N-type material, anode, cathode. Okay. So it is a. So it is look like this. So it is a P. It is N. General diode means here Z. It will look like Z. General diode. Next, next, next. So here you know materials can be classified as conductor, semiconductor, insulator. Just now I explained. Next, Ellen. See this you know in intermediate. Okay, what it mean by energy band? How it will look like in the conductor, semiconductor, insulator. Next, Ellen. Next, next, sir. Next, next. Avannoddu. Next. అది కూడా వద్దు. Next, 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 next. So ఇక్కడ left. Previous. So here, see, semiconductors are classified as intrinsic semiconductor, extrinsic semiconductor. So what is mean by extrinsic semiconductor? Adding impurities. Adding impurities to the intrinsic semiconductor will become extrinsic semiconductor. Okay, which material I am adding? Which material I am adding? Depending upon the adding of that material. That means trivalent atom materials we are adding to the intrinsic semiconductor, then it will become P-type material. Whenever I am adding pentavalent materials to the intrinsic semiconductor will become N-type material. Okay, next. So here See, examples of the semiconductor is nothing but here silicon and germanium. So they look like this. Idem avasam ledu, just you want to know about okay. Next, next. See, pentavalent impurity atom having 5 valence electrons. That will become now. So examples are phosphorus, arsenic, antimony, bismuth. These elements, pentavalent elements, is adding to the germanium and silicon, which will become one type of material. Next, next. So here three valent, trivalent, the three valent electrons like boron, aluminum, gallium, indium is adding to the intensive semiconductor which will become okay. Tri means p type and 5 means n type. Next. So it is not internal structure is not required. Next, LND. Next. PN junction diode అని వస్తుంది చూడండి. What is mean by PN junction diode? It is C. What is mean by biasing? What is mean by biasing? Connection of external voltage source. Connection of external voltage source to the PN junction diode is known as biasing. So depending upon how we are connecting the okay external supply, that is positive terminal to the positive terminal to negative. So depending upon the way of connection of the voltage supply to the PN junction diode, we are classified as forward bias PN junction diode and reverse bias PN junction diode. Okay. So here, see, everything just now what I explained, that is there. Next. So here, see, so here it is a P-type material, it is a N-type material. Contact surface is called depletion region. Okay, it is a P-type material, total P-type material, it is N-type material. So actually, so in P-type material, okay, holes are the majority charge carriers. Okay, you know, inside what happens actually, charge will move, electrons will move, holes will move. So who will take the charge? So in P-type material, holes will is the majority charge carriers. In a N-type material, electrons are the majority charge carriers. So what happens actually, which is look like, see, we'll say it is anode, it is cathode. Two terminal names of the diode is anode and cathode. That is called P type and N type. P is not a positive, N means negative. No. P means P type material, N means N type material. Okay? Right. The terminal names are anode and cathode. Okay. So whenever this P-type material is joined or sandwiched to N-type material, which will form the PN junction diode. Okay. What are the majority charge carriers here? Holes are the majority charge carriers. Here, electrons are the majority charge carriers in the N-type material. Okay. So the contact surface for P and N-type, which will form the depletion region. Okay. So depletion region means contact P-type material, N-type material. This contact surface is called junction. This contact surface is called PN junction diode. Now, what it mean by P, what it mean by N, what it mean by PN junction diode, just now I explained. Now, if I connect this PN junction diode in forward bias mode, what happens? If I connect this PN junction diode in reverse bias mode, what happens? Okay, so let's next. Yes. So this is forward bias mode. Forward bias mode means whenever voltage supply positive terminal is connected to the positive terminal, that means P type material. Okay, and negative terminal is connected to the negative, that is N type material, which forms the forward bias. This connection is known as, whenever positive terminal is connected to P type and negative terminal is connected to the N type. Okay, this way of connection is called as forward bias forward bias mode. Okay. So forward bias mode. So here, here see what I mean by positive, positive, positive charge. Here minus negative charge. Okay. So here holes is having positive charge. Holes is having positive charge. Electrons is having negative charge. What happens? Voltage I am applying. Initially it is 0. I am increasing the voltage 0, 1, 2, 3, 4, 5, 6, 7. Initially 0. So I am increasing the voltage. What happens? Like poles ripple, like charges ripple. Plus and plus, what happens? Like pole ripple. Whenever plus comes, what happens? It is ripple. It is going. Okay. So like charges will ripple. Okay. So whenever this positive supply is given to the p-type, these holes which are in the p-type material will will repel each other. Will So here see positive charge I am applying, holes are there here. So because of the both are positive, so these holes will move from here to here like this, here to here. So holes will move to P type to N type material. Okay. So the holes which are moving from the junction to P type to N type, okay, they will recombine with electrons. The holes which are in the P type material will recombine with the electrons, and then these holes will now renamed as electrons. Holes which are recombined with the, see, this will jump from here to here. All the holes are jump from P type to N type material, and these electrons will recombine each other with the holes, and these holes will become electrons. Okay, like this, as the voltage is increasing from okay, 0 to increasing value, at certain voltage, these holes will jump the jump the or crosses the PN junction. Okay, at the time, at what time, at a what voltage it is crossing that voltage. Okay, the voltage at which the voltage at which the holes are crossing from P type to N type material. The voltage, okay, voltage at which the holes are crossing from P type to N type material. That voltage is known as cut-in voltage. Cut-in voltage. Up to that voltage, there is no crossing of holes. There is no conduction. Okay, holes are here, electrons here. But whenever I am increasing the voltage, what happens? Whenever I am increasing the voltage, what happens? These holes are crossing the, like this it is going, holes are going like this. And so negative supply, see, negative supply is connected to the electrons. So here also like poles are repel, like poles are repel. So whatever the electrons are available, because of this negative and electrons are negative, this will move forward here. So this will, now electrons will jump from a N type to P type. Electrons will jump from N type to P type. Okay, P type to N type. Then, okay, what happens? The electrons will recombine with the P type materials. Electrons will be recombined with the P type material. Thereby, see, holes are moving like this, electrons are moving like this. Okay, P to N and N to P. So there is a continuity of supply. There is a continuity of supply. Okay, so these are moving like this. Holes are moving, jumping from P to N type. Electrons are, because of like poles are repel, electrons are also moving like this. So there is a continuity of supply like this. It is moving like this, it is moving like this. So there is a continuity of supply of positive to negative. Okay, they are interacting like this. Okay, so this is known as forward bias. So if we draw the characteristics of the curve for this, okay, move to next page, next page, next page, next page, next page, next page. Yes, if we draw the forward bias characteristics, okay, it is the voltage, forward voltage, it is the current. The current, amount of current which is flowing through the diode. The amount of current which is flowing through the diode. So see, At the time of voltage V is equal 0, there is no current here. Current is 0. As the value of voltage increasing, at the certain voltage of V gamma, that is cut-in voltage, V gamma, so the current starts flowing. The current starts flowing and increasing rapidly. This is known as forward bias characteristics. Forward bias, okay, that characteristic curve which is drawn between forward voltage and forward current. That curve is known as forward bias characteristics curve. Next, reverse bias. Okay, so reverse bias. Reverse bias means simple. See, whenever negative supply is connected to P-type material, whenever positive supply connected to the negative negative terminal, which forms the reverse biasing of PN junction diode. See here, simple it is. Okay, whenever we are connecting negative supply to the P-type material, whenever positive supply is connected to the electrons, so this negative supply is having, okay, negative supply means negative charge. So holes are having positive charge. So like poles, okay, here unlike poles. Like poles repel. It's unlike poles. So negative, positive. What happens? These holes are attracted by this negative charge. Holes are attracted by the negative charge. Here, positive supply. Here electrons are negative. What happens? These electrons are attracted by the positive supply. What happens actually? Because of initially it is 0. I'm increasing the voltage. I'm increasing the voltage. What happens? This, whatever the holes are there, where they are moving towards the, okay, negative supply. Why? Because holes are positive supply. These are moving towards the, like this. And whatever the electrons are there, because you are applied the positive, they are moving like this. So what happens actually? These are not flowing like this. Now these holes are moving here and electrons are moving here. There is no continuous supply. There is a huge gap between this. Yes, like this they are going now. So what is happening? So there is a increasing of depletion region. There is no continuity. Okay. So here you applied the negative value. So here like this. Here it is like this. So there is no continuity supply. Like this, they are not moving. These are moving like this. These are moving like this. There is no continuity of supply. Then in reverse bias mode, diode will be act as the off position. Okay. Next characteristics. Next curve. So in reverse bias mode, okay, the curve is like this. So this is reverse current. This is reverse voltage. So for example, what? So the here in a PN junction diode, we will get avalanche breakdown. So there is a value of voltage where voltage is I am increasing. Increasing voltage. What happens? The depletion region, as the voltage is increasing, the depletion region, okay, previously like this, the depletion region is increasing. So there is a point where the diode is breaking down. Why? Because the electrons and the holes will reach the saturation level. That saturation level, the point of where the diode is breaking down, that is known as avalanche breakdown. Avalanche breakdown. The diode will breaks physically. Physically, diode will breaks. Why? Because I am giving the huge amount of voltage in negative way. So depletion region increasing. At the certain point, it will break down. That is called as avalanche breakdown. Okay, right. Next. So uh, in PN junction diode, we will find out the, okay, static resistance and dynamic resistance. In PN junction diode, we will find out the uh, static resistance and dynamic resistance. Okay. So what is meant by static resistance? Static resistance is nothing but DC resistance. Okay, static resistance is known as DC resistance and dynamic resistance is known as AC resistance. The amount of DC resistance contains in the diode is known as DC resistance. The amount of AC resistance available in the diode is known as AC resistance. Okay, that is dynamic resistance. Dynamic resistance is nothing but AC resistance. Static resistance is nothing but DC resistance. Static means constant. Constant means DC always constant. So we'll find out the DC resistance and AC resistance in forward bias mode. Okay, what is the formula for DC resistance? Forward voltage by forward current. Okay, forward voltage by forward current. Next slide. Next slide. Mm. So static resistance, forward voltage by forward current is nothing but static resistance, and we'll find out dynamic resistance. Dynamic resistance can be obtained by two continuity of voltages in reverse bias mode. Okay, two not forward bias mode only. So two continuity of the voltages of VF1, VF2 minus VF1 or VF4 minus VF3 by IF4 minus IF5. We'll take two voltages in forward bias mode. We'll subtract from two continuity. Okay, V4 minus V3 by I4 minus I3. V by I is nothing but R. Why? Because Ohm's law, R is equal to V by I. So static resistance V by I. So dynamic resistance is nothing but V4 minus V3 by I4 minus I3. That is AC resistance. So amount of AC resistance available in the circuit is nothing but AC. Okay, is nothing but dynamic resistance. Okay. Now in next, this can be obtained in a static resistance. Next, forward bias dynamic resistance, that is AC resistance. Okay, next. In reverse bias, no, back, that is okay. Forward kellu. Next, forward, munduki, itu. Next. See here, reverse resistance. Reverse resistance means the resistance which is obtained in the value is in mega ohms. Why? Because if resistance is high, what happens to current? Resistance is infinity. What happens to current? Resistance is equal to infinity. What happens to current? Current is zero. Resistance is zero. Current is infinity. Resistance is zero. Current is infinity. Resistance is infinity. Current is zero. So reverse resistance, the resistance which is obtained in a reverse bias mode, reverse voltage by reverse current is nothing but reverse resistance. This reverse resistance is in very huge value. It is in mega ohm, 10 to the power of 6. Okay, right. So this is about the total characteristics about PN junction diode. Okay, next we'll move to the Zener diode. Next. This is previous. Yes. See, so diode in forward bias, it is like continuity. Diode in reverse bias, it is like discontinuity. Just now, depending upon this only, this diode action only. Okay, diode is used in rectifiers to act as the switch, on switch and off switch. Okay, right. Next. So diode is used as electronic switch. Next. No, malla tell no. Next. So these are the applications of the diode. Diode is used as the electronic switch. It is used as the rectifier. It is used as the clippers and clampers. Okay, and voltage multiplier circuits also diode will be used. Okay, so everywhere we will use the diode. No need to worry for that. Next. Zener diode. So what is meant by Zener diode? So actually, what is the disadvantage of diode? Diode will not conduct in a reverse bias mode. So in certain applications, I require to operate the in a reverse bias mode also. Diode will not conduct in reverse bias mode. Yes. So in certain operations, I require to operate in reverse bias mode also. So I required additional, okay, equipment, additional, okay, additional, okay, that materials to act as the diode as one more name. That diode is known as Zener diode. What are the disadvantages are there in the Zener diode that can be reduced to in a Zener diode? Whatever the disadvantage, diode cannot be act in reverse bias mode. So this Zener diode will be function in a forward bias mode as well as reverse bias mode. Okay, diode will be act as diode will be act as forward bias on, reverse bias off, whereas Zener diode will be act in forward bias on, reverse bias on. So what are the modification is required to, okay, manufacture the Zener diode means? So Zener diode is nothing but it is a heavily doped diode. What is meant by doping? What is the meaning of doping? Define doping. What is meant by doping? Doping. One more question will get. What is meant by doping? Yes, adding of impurities to the intrinsic semiconductor is known as doping. Or you can say process of adding of impurities to the intrinsic semiconductor is known as doping. So here I am adding more impurities. I am adding more impurities such that the doping is more, okay, more doping. So heavily doped you can say. So Zener diode is a heavily doped diode. It is a diode only, okay, but because of it is heavily doped, you can call it as Zener diode. Okay, more impurities are there. So same Zener diode, whatever the diode forward bias characteristics only. What are the disadvantages of diode? It will not conduct reverse bias. So Zener diode will conduct in a reverse bias mode. Zener diode will conduct in a reverse bias mode also. So whatever the forward bias characteristics are there, that holds good for Zener diode forward bias characteristics. Exactly whatever the forward bias characteristics are holds good for a PN junction diode as well as Zener diode, that is holds good for negative. So simple, Zener diode will also conduct in a reverse bias mode. Whatever the forward bias mode is there, same reverse bias mode, same characteristics will get. Next go. Next. ఇవన్నీ అవసరం లేదు అయిపోయింది. The symbol of the Zener diode is like this. So their PN junction diode will get only line. Here will get Z. It is like Z. That's why Zener diode. So here also name, same name, anode, cathode, PN junction. Why we are calling as a Zener diode? It will conduct in a reverse bias mode also. It will conduct in reverse bias mode also. Okay, right. Next. Same. Uh, Forward bias of PN junction diode is equal to Zener diode forward bias. Next you go. Same. Whatever the curve we are obtaining in the PN junction forward bias characteristics, we will get same curve in the forward bias of Zener diode. There is no different. Next. Next. Uh, Next. So here okay, Zener diode or reverse bias of Zener diode. So reverse bias Zener diode means here, okay, we'll get a output as the same current. Okay. So Zener diode also conducts in reverse bias mode. Okay. In forward bias mode it will conduct, reverse bias mode also it will conduct. Next move. Move. ఇదంతా అయిపోయింది. So I will share these notes, okay, to the sir. That sir is there, na? I will, okay, kindly uh, be study for that. Okay. Next. So here, so once you see the syllabus, what are the topics we have to cover? What are the topics we have to cover? So, see, once again, I am repeating what are the topics which are in part B. So, part B, unit 3. Unit 3, detail electronics, everything is over except flip-flop. Except flip-flop. And unit 2, okay, block diagram representation of DC power supply, okay, working of full wave bridge rectifier. Rectifier is over? Yes. Capacitor filter, working of, this is not over. Uh, Public address system, circuit diagram and working of, okay, RC coupled amplifier, over, okay. Here, logic gates is over, universal, unit 3, BCD code, XS3 code, gray code, Hamming code, okay, theorems and gates. Here, we didn't cover the flip-flops, registers and counters. So almost all in second unit, everything is over. Second unit, third unit also, except flip-flops, everything is over. Unit 1, PN junction diode and Zener diode also over. Here we have to study BJT. BJT, okay, elementary treatment only. బీజేటీ ఉంటుంది చూడండి అక్కడ నెక్స్ట్ ఉందా బీజేటీ ఇదిగోండి బీజేటీ అవునండి ఇదే ఉండండి previous so here we'll move on to the transistor that is called as bipolar junction transistor. Two diodes connected opposite which will form the bipolar junction transistor. Why you are saying bipolar junction? What is the meaning of bipolar? Here the flow of the current, the major current, okay, which is flowing through the transistor will take place both majority charge carriers as well as minority charge carriers. So because of the, okay, majority charge carriers and majority and minority charge carriers is responsible to flow the current. So that's why you can say bipolar junction transistor. So it is a 3-terminal device. Bipolar junction transistor means it is a 3-terminal device. It is act as the switch in the electronic circuits. Okay, BJT transistor, bipolar junction transistor. Bipolar junction transistor means here you will get 2 junctions. Okay, so 2 PN oppositely connected, which will form the bipolar junction transistor. Here we are having 3 terminals named as emitter, base, collector. So 3 terminals are there for the BJT, that is called emitter, base, collector. See, next you go. Next. So depending upon the construction of the transistor, we can name it as the NPN transistor and PNP transistor. NPN transistor and PNP transistor. PN, 2 diodes, PN. What happens? There is a combination. If it is add to oppositely, what happens? PNP. N is common here. NPN, P is common. 2 diodes oppositely connected which forms the diode. Okay? A transistor. Next. Like this. See. PN. PN. What is the common here? N is common. N is common. So whatever the common, okay, we will pick one terminal for that common. One is P type, one is here P type. So how many terminals are there? 1, 2, 3. So this is called emitter. This is called, okay, base. Other one is called collector. So emitter, base, common. So this transistor can be operated as, okay, nearly 4 ways. Transistor can be operated in 4 regions. Transistor can be operated in 4 regions. What are they? active region, reverse active region, cutoff region, other one is saturation region. Okay, so here see how many terminals are there? Three terminals are there. Three terminals, emitter, base, capacitor, collector. Emitter, base, collector. Now, depending upon the, okay, connection, depending upon the connection. So, we require two as the input. We require two as the output. We require two as the input and two as the output. Okay. So, for example, I am taking emitter plus, base negative, plus minus. Two are the terminals, input terminal. And output terminals, collector plus, base negative. So, base is the common. Base is the common for the transistor. So, we can call it as common base configuration, common emitter configuration, common collector configuration. So we can connect the transistor in three ways: common base configuration, common collector configuration, common emitter configuration. So depending upon these three configuration, the transistor is having its own input characteristics and output characteristics. So this transistor can be operated in how many ways? How many modes? Operated in four modes. One is active region, second one is reverse active region, okay. Another one is cutoff region, another one is saturation region. Four regions you can operate. So on what way? How can you operate this transistor as the active region? How can we operate? Next, next. నెక్స్ట్ 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 ఇది కాదు ఒకటి ఉంటుంది ఫైనల్గా నెక్స్ట్ 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 సో దిస్ వన్ సో transistor is operated in four ways. One is called active region, saturation region, cutoff region, inverse active. So whenever see what I mean by forward bias, do you know what I mean by forward bias? When p type material is connected to the positive terminal, n type material is connected to the negative terminal, then it is called as forward bias. When n type p type material is connected to negative and n type material is connected to positive, then you can say reverse bias. Okay, so depending upon this forward bias connection, how many are there? PNP, PNP. Okay, how many voltages we have to apply? Input voltage, output voltage. You have to apply two voltages. Why? Because how many junctions are there? Two junctions are there. J1, J2 junctions are there. PN, PN. PN, forward bias mode. NP, reverse bias mode. So, if emitter base junction, see, if emitter base junction is connected to forward bias mode and collector base junction is connected in reverse bias mode, then the transistor will be act as the active region. అక్కడ అదే ఉంది చూడండి, active region. Okay, so our aim is to operate transistor in the active region. Okay, emitter base junction is forward bias and collector base junction is reverse bias, then you can say it is in a active mode. Okay, for example, you connected reverse, you connected reverse means emitter base junction is connected as reverse bias and collector base junction connected in forward bias, then inverse active, exact opposite. So inverse active region. Okay, so now cutoff region, cutoff region, cutoff region means both. Okay, cutoff region and saturation region. Cutoff region means emitter base junction is connected reverse bias mode. Cutoff region means emitter base junction is connected in reverse bias mode and collector base junction mode connected in reverse bias mode. Then the transistor will be act as the cutoff region. Cutoff region means there will not be operation. There will not be operation. Minimum operation. Okay, and saturation region. Saturation means there is tending to for breaking of the transistor. Saturation region, saturation level, it is tending to damage. At what position? If the emitter base junction and collector base junction connected both are in forward bias mode. Okay, Emitter base junction is connected in forward bias mode, collector base junction connected in forward bias mode, then the transistor will be act as the saturation region. Okay, next. So depending upon the common connection from the input and output, we can classify these transistors as common base configuration, common collector configuration, common emitter configuration. Next. So this is the common base configuration. Common base means, see here, so base, emitter, collector, base, emitter, collector. Why we require these resistors here? RE, RC. Why we require these resistors? See, emitter base, PN, for example, PNP transistor, emitter base junction is connected to forward bias. See, forward bias, plus terminal is connected to the P type and negative terminal is connected to the N type. Okay, forward bias. See here, it is a reverse bias. Base, collector base is in reverse. See, P is connected to negative, N is connected to positive, reverse bias. So this is the uh, common base transistor configuration in a active region. So in order to convert this one into saturation region, how we have to convert? Both are should be forward bias mode. This is forward bias mode, this is forward bias mode. Okay, okay. So this is about configuration. Why we require these resistors? The two resistors. Okay, whenever we are connecting voltage supply and voltage supply, okay, in order to limit the current through the circuit, in order to limit the current through the circuit, we require resistors here. Emitter resistor, capacitive resistor. These two will protect the transistor. Only protection purpose we are using these resistors. RE and RC. Protect the, okay, in order to avoid the damage of transistor, we have to use the resistors here. Emitter resistor and a capacitor resistor. How many voltages are there? How many? Emitter base voltage is there. Common base voltage is there. So collector base. Collector base voltage and emitter base voltage is there. So depending upon the how this voltage is applying input voltage, this is input voltage, this is output voltage. Okay, input current, emitter current, output current, collector current. How many currents are there? Base current is there, current is flowing through the base. Emitter current is there, current is flowing through the emitter. Current, collector current is there, current is flowing to the collector junction. Current will flow like this. Emitter current will flow here like this. Base current will flow like this. So collector current. So the voltage between emitter and base junction is called emitter base voltage, and the voltage in between collector and base called collector base voltage. So depending upon the how these voltages and current acts in the transistor, okay, we will get the input characteristics and output characteristics. Next, characteristics ఉంటాయి. Next, so these are the characteristics of CB configuration. So CB configuration is very, very important. So that's why CB configuration. Input characteristics means input voltage, input current. What is the input voltage? Emitter base voltage. What is the current? Emitter current. See here. So collector base voltage is, this is the emitter base voltage. It is 0 to infinity. I am increasing. So what is the emitter current here? Emitter current. Input voltage and input current. If we draw the curve in between input voltage, input current, which will become input characteristics. If we draw the curve, output voltage, output current. Output voltage is collector base current voltage and collector current. Then we can say it is a output characteristics. So depending upon the voltage, as the voltage is increasing, emitter base voltage increasing, there is a cut-in voltage at where this, okay, emitter base PN junction diode, okay. So it will not conduct after the point of 0.6 minimum voltage. This emitter base junction are the, okay, the current will flow from the emitter to emitter to base. Okay, that current is known as emitter. Okay, emitter current. So see, the current is flowing here. So at what value? So at what value we are having the output voltage, that is collector base voltage. Okay, at a collector base voltage, we are having input characteristics as well as output characteristics. So this is about common base. Okay, you take 5 minutes break. We'll continue. Common collector, common emitter. Only this diagram and the characteristics you have to explain. Okay, we'll take 5 minutes break. Hello. So this is about CB configuration. Okay, where we will get the input characteristics for the input voltage and input current. What is input voltage for CB configuration? Emitter base voltage and emitter current is the input voltage. What is the output voltage? Collector base voltage and collector current is the output. See here, collector base voltage, collector current. Okay, so this is ordinary our PNP transistor forward bias is there. That is for a different value of output voltage VCB. Okay, emitter base for the output voltage for the different current. So whenever we are giving as the input voltage, whenever we are giving or we are changing the input voltage with respect to emitter base voltage, okay, at certain voltage emitter current is 0. What is that current here up to here? See here. So after that only, after increasing the emitter base voltage, what happens? Simple PN junction transistor forward bias. So increasing. So this is about input characteristics, input voltage, input current. So output. So this output is depending upon the how much emitter, how much input current is there. So output characteristics, that means output voltage, that is emitter base voltage, and collector current is depending upon the how much input current we are giving. So see here, collector base voltage, collector current. So output current is depending upon the ఏమైంది is depending upon the how much input current. So input current is 0. What is that? Input current is 0. Even we are giving collector base voltage. So this is collector current. So there is a minimum of current collector current. So for example, emitter current input current is 0. How much collector current here? So this is collector current. As the emitter current, input current is increasing, so as the different values of input current, what happens? Collector current varies. As the input current varies, what happens to collector current? Current varies like this. So for different emitter current, as the value of emitter current increases, so this collector current increases. Collector current, this is the curve for collector current. Input voltage, output voltage. What is output voltage? Collector base voltage. Or what is the output current? Collector current. So different value of input current. Okay, we are getting the collector current like this. So whenever emitter current is 0, okay. So collector current, emitter current is 0. That region is known as cutoff region. Whenever emitter current, that is input current, will reach or tends to infinity, then that level is known as saturation level. Okay, see, IE is increasing, IE is increasing. So this region is there. This region is called, okay, saturation region. This region is called up to here. So wherever the mark is there, na, this is called saturation region. This is called cutoff region. And in between this is called active region. Okay, so this is about a common base configuration. Just you have to explain. Sir, previous kellara previous అది కాదు కదా ఇది ఎక్కడిది అందులో కామన్ బేస్ సో ప్రీవియస్ దాంట్లో ముందు సర్క్యూట్ డయాగ్రామ్ ఉంటుంది సర్క్యూట్ ముందు అది దట్స్ సో దిస్ ఇస్ ది సర్క్యూట్ డయాగ్రామ్ యూ హ్యావ్ టు డ్రా దిస్ సర్క్యూట్ డయాగ్రామ్ సింపుల్ it should be in active region. It should be in active region. What we have to do? It is a PNP transistor. emitter base should be forward bias. Active region, forward bias. Forward bias means here VEB should be positive. So see, EB positive, positive, negative, forward bias. And collector base should be reverse bias. See here, collector, negative, base, positive. This you have to keep in mind. Okay, that one diagram is there. Total uh, emitter base should be forward bias, collector base should be reverse bias. Then only transistor will be act as the active region. Inverse active region means exactly opposite, cutoff region. Okay, saturation region. Okay, next LND. So same. So these all the common base configuration is over. Next, common emitter as well as common collector circuit diagram as well as the input and output characteristics you have to know. Next. This is a common base is over. Next. Common emitter? Yes, common emitter configuration. This is the common emitter configuration. Emitter, see, emitter is given to the input negative, emitter is given to the output. Okay. So common is emitter here. See, common is emitter is given to input, emitter is given to output. So here also same. In order to become the transistor of common emitter configuration should be inactive. Okay. Emitter base junction should be forward bias. Emitter base junction should be forward bias. See, emitter base junction should be forward bias. Forward bias means plus minus. And a collector base. So collector base means here collector emitter should be forward bias as well as this one is a reverse bias. So here, see here plus and minus. Okay, one is common emitter is common emitter. Okay, so input is negative and output is negative. So we'll call it why we require these two resistors, this RB and RC, to in order to protect the transistor we require the resistors. Okay, so for example for this the diagram. Next. Next. So here also same. These are the common emitter configuration. Whatever the common base configurations are there, same configuration for this. Same, there is no change. Same. Okay. Next. See, here also same. What is the different? Common emitter, common base. What is the different? No different, but the voltage level is different. Okay. Here see, common collector emitter voltage. The output is where we are getting output. Output we are getting at a common collector, not common collector. So here there is a voltage of collector emitter voltage and a collector current. See, collector current is the output. So output voltage, output current. The curve which is drawn between output voltage and output current is known as output characteristics curve. So see here, what is this? Emitter base voltage, IB. So different values of base voltages. Base voltage is nothing but this is the input voltage. See, this is the input voltage. Base voltage here, input voltage. Input voltage, as there is no input voltage because of there is no input current, there is no input voltage. So this in between this is known as, so IB0 to this one is known as cutoff region. This is known as cutoff region, and this region is known as from here to here. This region is known as saturation region, and in between this total region is known as active region. Okay, same. Okay, next నేను అది పెట్టాను చూడండి, అది పెట్టండి, ఇది తీసేయండి, నేను పెట్టాను చూడండి, వాట్సాప్లో షేర్ చేశా కదా. Right. Okay. So common emitter, common base, common collector configuration. Okay. Kindly read. I will share these notes. Only you have to draw the diagram and input characteristics, output characteristics you have to explain. Okay. Otherwise, ఇది క్లోజ్ చేయండి. అది వేయండి. Right. Now, there is a topic is called adders. Adders. Okay. Half adder and full adder. What is the difference between half adder and full adder? Means half adder means 1 bit. 1 bit. We can add the 1 bit only. We can add 1 bit. Okay. Whereas full adder means you can add the 2 bits. Binary addition, 1 bit means what is the meaning of 1 bit? 0, 1. This is 1 bit. 0 plus 1 is how much? 1. Okay. 0 plus 0 is how much? 0. 1 plus 0, 1. And 1 plus 1, 0, 1. Okay. Whenever we add the 1 bit data, okay, okay, addition, binary addition can be done by the one circuit. The binary addition. That addition is known as adder. So depending upon the how many bits we are using, that is nothing but half adder as well as full adder circuits. Half adder means 1 bit addition, 1 bit addition. Full adder means 2 bit addition, 2 bit addition. Okay. So see here, A plus B. A is the input, B is the input. Simple. So this is A, this is B. Okay. This is A, this is B. 0 plus 0, sum. What is carry? 0. 0 plus 1. What is sum? 1. What is carry? 0. 1 plus 0, 1. What is sum? 1. 1. Carry? 0. Here, 1 plus 1. Sum is 0, carry is 1. That is explained here. Yes? 0 plus 0, 0. 0 plus 1, 1. 1 plus 0, 1. 1 plus 1, 0 and 1. So, there is a 2 terms are there. What is that? One is sum, other one is carry. So, this is term, sum. Carry is here. Okay. So, if we draw this is half adder circuit. Half adder circuit. Half adder means 1 bit data you are adding. You are manufacturing or you are implementing one circuit diagram, okay, which is known as half adder circuit. Half adder circuit. So half adder circuit is nothing but which will add the 1 bit data. 1 bit data. Okay. So now see. So here see 0 plus 0, 0, 0, 0. Now here I am making one sum equation. Some equation. So this is the output, okay? This is the output, some output. What is the, which truth table it is? Which truth table? 0, 1, 1, 0. And the truth table? 0, 1, 1, 0. And the truth table? Output. You know the truth tables of AND gate, OR gate, NOR gate, NAND gate, NOR gate, exclusive OR gate, and exclusive NOR gates. Output. So this is 0, 1, 1, 0. What is the output? Which gate output? XOR gate. Or you can write C. A bar B. A B bar. Yes. So sum output is A bar B plus A B bar, which is known as XOR gate. Sum is, we implemented some equation as A bar B plus A B bar. That is A exclusive or B. This is a sum. You are developing the circuit now. Half adder circuit you are developing. Okay. Now carry. What is the equation? A bar B bar. Yes. One where we are getting A bar B bar. Here A means 0, A bar means 1. B means 0, B bar means 1. Like that. Okay. So you implemented, you got in order to add the 1 bit data. Okay. 0 plus 0, 0 plus 1, 1 plus 0, 1 plus 1. You got 2 equations. Depending upon these equations, you have to develop the circuit diagram. What is the circuit diagram? Okay, see here. So whatever I written here, whatever I written, same thing, okay. Adottu cheptam. Okay, whatever I have written, okay, that equation, see, which is matched with this. Yes? Okay. This is A bar B. It may be A B they are saying. It may be A bar B bar, or depending upon what you are taking, whether we are taking A is equal to 0 or whether you are taking A is equal to 1, it is A bar B bar will become. Okay. Right. You take A B. Okay. Now for this, if you take A is equal to 1, A bar is equal to 0, or A is equal to 0, A bar is equal to 1, that is up to you. No need to worry for that. Okay. Now for this, you require a circuit diagram. Okay. A and B. Exclusive R. Okay. You have to get the output as exclusive R. So here, see. Hmm? So output you are getting as sum, which is nothing but A bar B plus A B bar. Okay. Now sum is AB. Sum carry is AB. You take a A. You take a B. AB. AB means AND gate. AB means AND gate. Carry. So this is the circuit. This is half adder circuit. Pattern. So this is the half adder circuit. Whatever we implemented, this is half adder circuit. Okay. It is same way now. Full adder. Full adder. Full adder is nothing but we can add the 2-bit data. This one. This one. So full adder circuit. రాసుకోరా అమ్మా ఇది. So here full adder will take, instead of taking ABC, will say as, it is a 2-bit actually. It is a 2-bit addition. 2-bit addition. 2-bit, what is the meaning of 2-bit addition? 0, 0 with respect to 0, 1. What is the output? 1, 0. For example, in 2-bit addition, 0, 1, 1, 1. What will get here? 2-bit addition. 1, 1, 0, 1. 1 plus 1, 0, 1. See, here you are you getting one carry for 2-bit addition. R 1, 1, 1, 1. 1 plus 1, 0, 1. 1 plus 1, 0, 1 and 1. 1, 1. So this is carry. For 2-bit addition, we are getting one carry. Here 0 carry. Here we are having carry. So that's why I have taken as the inputs are 3. AB and carry. AB and carry. So you know about 3-bit maximum value how much? 1, 1, 1. What is the maximum value? 7. Yes. So 7 I have drawn. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 0, then 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1. For these inputs, it's the addition. Okay, addition 0 plus 0, how much? Like that. Okay. So 0 plus 0 plus 0 is 0. 0 plus 0 plus 1 is 1. 0 plus 1 plus 1. So it is here 0 and carry 1. 1 plus 1 how much? 0 and carry 1. So 1 plus 0 and 0 is 1 and 0. 1 plus 0 is 2. So 0 and 1. Wherever the 1 1. Wherever the two ones are there, we'll get a 0 and 1. 3 are there, it will get a 1 1. Okay. Now this is the truth table for full adder circuit. Truth table for full adder circuit. Okay. Truth table for full adder circuit. Now we have to implement, okay, sum. What is the sum equation? This is the sum equation. What is the carry equation? This is the carry equation. So there are two outputs. One is sum output, and one is carry output. So sum output you draw. Okay, this one where we are obtained here. See, this is 0 1 0 1 0. B bar 0 means bar. 1 means A. Okay, right. Now here see, one is there, one is there. A bar, B bar, C plus A, A bar, B, C bar. Then A, B bar, C in bar. A bar, A, B, C in. Same equation which is implemented by truth table. Implemented by truth table. Now, can we take common here? You can take A bar common here. A bar is a common. B bar C in plus B C in bar. Okay. You can take A is common here. B bar C bar in plus B C in. See, it is exclusive OR. A bar B plus A B bar. Exclusive OR output. So here B plus C in exclusive OR. As well as here C. Here BC whole bar plus BC. It is exclusive NOR. Exclusive NOR. This is exclusive NOR. It is exclusive OR. Okay. Both should be addition. So there is a common of A bar and A. Okay. This is about sum output. So if you take this total common, you will get a sum output as A exclusive R of B of exclusive bar of C. This is the sum input. Next. Then we'll move to the carry. Carry. Where we are getting one we are getting at A bar B C in and A B bar C in and A B C bar and here A B C in. C. In the same way, I am taking common. AB is the common here. So we'll get C in plus C in bar. Here AB. Okay. AB common. AB is there, AB is there, common. So C in I am taking. So we'll get A bar B plus AB bar. So this is the exclusive R. Okay. So by taking AB, so here we know A plus A bar how much? 1. A plus A bar 1. Last class we studied A plus A bar how much? 1. So C in plus C in bar is becoming 1. So we got only AB. So here this is exclusive R. A bar B plus AB bar. So C in of A exclusive R of B. So final output is, you can write like this. C output is AB plus B C in plus A C in. This is the output of C output. Next. Right. So some implementation is like this. Some output is A bar A exclusive bar of B of exclusive bar of C. See, AB exclusive bar plus C exclusive bar. So this is the sum output circuit diagram. Sum output. A exclusive bar of B exclusive bar of C in. Sum output circuit diagram is this. Next, carry output. So here this is sum output. This is carry output. So see here, AB plus Cn plus AB exclusive R. Okay, if you do this, you will get a C output. Okay, total implementation. AB plus C in AB exclusive R. R AB plus BC in plus AC in. Same. AB, BC in, AC in, and by taking R. Yes, AB plus BC in plus AC in of R. Plus indicates R. Here, what is the value here? AB. Here, B, C in. Here, AC in. Here, it is R. R gate means AB plus BC in plus AC in. This is carry output. So this is the circuit diagram of carry out. This is the circuit diagram of sum. Okay, you can add this both circuit diagram which will implement a single circuit diagram which is known as full adder circuit diagram. Okay, that can be drawn here. అదొద్దు అది ఇంత ముందే పెట్టండి which can be implemented like this. Okay, A is here, B is here, C is here. Okay, draw 3 like this. Okay, so now here this is sum output. Okay, where we are getting here A, B, and C. Okay, it is A, B, C. It is sum output. Now this one. So from A and B. B. Okay, and B and C in. And A, అయిపోయింది. So this is about so this is about a full adder. So half adder, full adder. Over.